Hello, welcome to C++ London, the lockdown edition. So we are streaming live on YouTube, unless of course you're watching the recording.
Hello,
in which case we
London,
did watch.
the lockdown
Hang on a minute.
edition. So we are streaming live on YouTube, unless of course you're watching the recording.
First problem we've had already is my laptop muted. Thought it was. So here we go again. C++ London lockdown edition, streaming on YouTube. We have a special guest this evening, who was originally meant to be visiting us from Munich, but because of the change of circumstances, we cancelled that, and he's agreed to come back anyway and stream live. So move to the next slide. So we're going to introduce Klaus Iglberger in a moment, who's going to talk to us about no paradigm programming. Before we do that, just a little bit more news and a little bit about how we're going to run this as well. So we were actually meant to be here tonight, which is St Catherine's Docks in London, the site of Smarkets, who are going to be hosting us. This is where we were last year, so great photo. The weather's not quite like that tonight anyway. Of course, we can't be there. We are online instead. And next month, we were meant to be at Maven Securities, going to be a new host. Obviously, that's not going to happen either. But we're going to try and keep that date, and we're going to do another online event, assuming this goes okay. And I think we're going to be doing these online until further notice, and until things clear up sufficiently that it's going to be reasonable to hold an in-person event. Again, we're not going to predict when that's going to happen. So we're going to experiment with this format a bit and see how far we can push it. And I'll talk more about that in a moment. But first of all, I wanted to give a shout out to some other online meetups that are springing up. So some other meetups around Europe that you may not have been able to get to because of their locations. Well, now they're online, of course you can. So here's a few that are coming up soon that are close to our time zones. We've got the Munich C++ group, which incidentally Klaus is one of the organizers of. That's happening tomorrow, so maybe a little bit short notice, but if you can make that one, that's going to be worth getting to. And then the Gothenburg and Israel meetups, they're both on May the 5th, so you're going to have to choose which one you go for there. But I will point out that the core C++ one in Israel do lightning talks as well. We might try next time, actually. Didn't get it together for this one. If you do have any talks or ideas or anything you want to do, actually, for future events, whether in this online format or maybe for later, when we do go back to in-person events, do submit them to cpplondon.org/speak. Let's see the URL up on the screen now. There's a little form there to fill out. Doesn't have to be complete. It could just be a sketch of an idea. You're not committing to anything. It just shows me what people may be able to do. So as I say, if you want to hold off until we have physical events again, just put that in the notes at the bottom. If you do want to go online, but you're a bit unsure about how that works, because it is a little bit different, do talk to me. I can give coaching, walk through what the process is like. So don't let that be a barrier. We want to hear from everybody. Now, I mentioned that we're doing things a bit differently. If you haven't already gone to this URL, which I did put in the meetup and a few other places, live.cpplondon.org. It's just a little single page that I put together that aggregates together a few different services. So we have the stream that you're watching now, hopefully, maybe directly on YouTube or maybe on this very page. And that's embedded at the top. But then we have a few more, whoops, that's jumped too far ahead. A few more boxes down the bottom. Now you can just scroll through like that, but if you zoom out and ideally do this full screen, you should be able to get all the boxes on screen at once, and that's a much more comfortable way to do it. And then you'll see the bottom right, we have these Jitsi rooms. So video conferencing. This is just something I recorded earlier. Hello. If you click that tile icon, then it will toggle between tile view and current speaker. But more importantly, go to the settings and make sure in there you've set up your devices correctly if you're going to be chatting with other people. And also go to the profile and make sure you put your name in so people know who you are. And optionally, if you have a gravatar, you can put that in as well. Now, what I've done is I've actually set up a number of different Jitsi rooms because Jitsi works best if you have up to I'd actually say probably about 8 different people in there at once. So if it gets a bit crowded, just move on to another room. Maybe you can have different discussions in different rooms as well. So I'm trying to approximate what happens at an event afterwards when we go to the pub or wherever we go. Little groups will form around a particular discussion. Well, now we can do that here in Jitsi. It's an experiment. Don't know if it's going to work. It may be a complete failure. That's fine. Let's try it. So that's the Jitsi. But then I've also added this other box. Is that going to go there? Here we go. This is Slido, and you can ask questions on here, and then they'll come up in our view. You can actually vote on other people's questions as well. So the top voted questions we can answer first, and we can run some polls in there as well. We may do that in a moment. And then you'll notice that each of these boxes has an open externally button, just to open in a separate browser window, if that's the way you prefer it. Particularly if you have multiple displays, that may be a more comfortable way to do it. So this is the experiment. I've gone into it a little bit to try and make that a bit clearer. We'll see how it goes. And what I'm going to do now, we normally run the JetBrains raffle. Obviously, we can't do a raffle in person this time. So what I'm going to say is, if you're interested in winning a license to a JetBrains product, who are a sponsor, so it's a free license for a year, just send me an email, phil.nash@jetbrains.com, and in the subject just put 42, and then that's all you need to do. And I'll put your name in a hat, a virtual hat, and do the draw sometime tomorrow, and let you know if you win. Now, I mentioned that we have polls. Let me just come back out of here and take that off. I'm going to try and enable a poll now. It's the first time I've done this, so we'll see how it works. And it's just to get us warmed up. So I've put a poll in there now. Hopefully you can see it if you're looking at the aggregated view, just to ask whether you're a first timer or a regular, or if you're coming in from abroad. And I can see some answers coming in now, so it looks like that's working. That's good. I'll leave it up there for a moment because we can run that concurrently. Now what I'm going to do is pass over to Klaus in just a moment. When I do that, when he started, I'm going to put a different poll up, which is more closely related to what he's going to be talking about. And we'll see how that goes. So I'm going to introduce Klaus now. Hello, Klaus. Can you hear me okay?
I can hear you.
Great. Oh, the other thing I should have mentioned, by the way, this stream is about 10 seconds delayed after me and Klaus here actually talking. So if you're asking a question or responding to something, we may not get it in that same time frame. It shouldn't be too bad, but just to let you know. What I'm going to do is I'm going to drop off the stream and put Klaus's screen up, and then let him take over from here. So, hello, Klaus.
So, hello. A wonderful good evening. And many, many thanks to inviting me to the London C++ user group. I should perhaps first talk a little bit about how this came to be. So Phil is, in fact, one of our highlights at the Munich C++ user group. So Phil, correct me if I'm wrong, I believe for the past 4 years, you have been the last speaker every year. So our Christmas highlight, so to speak.
I'm not sure if that's last chronologically or in order of preference.
Of course, mean really highlight. So, but it has been 4 years, right?
I believe so, yeah.
So, and I've never been to the London user group. So you have a definitive advantage. You also sometimes work in Munich. I rarely go to London, but so this is my way of saying thank you for 4 years of great talks.
Thank you.
All right. So my topic today is embrace no paradigm programming. The first question you might have is, how came this talk to be? Oh, no, you may have one other question first. So who am I? So my name is Klaus. I'm actually doing C++ trainings since approximately 2016. This is not even enough C++ for me. I'm also doing C++ in my free time. I'm the main author of the so-called Blaze C++ Math Library. And as Phil already mentioned, I'm one of the organizers of the Munich C++ user group. Yeah, Phil already mentioned it. Tomorrow there's another talk. If you're interested, feel free to check it out. But about this talk. So how did it come to be? So I think we all agree that in the past decade, C++ has tremendously changed. There's a lot of new things, a lot of very, very cool new features. And this is what everybody is usually talking about, cool new features. So please teach us about move semantics, teach us about lambdas, teach about all the new stuff in C++. However, in these trainings, I also get an impression that very few people actually talk about software design. And to my astoundment, to some extent, there's still a very, very strong tendency to design software based on the teachings from, say, 20 years ago. So the things that I see, and the things that I talk about seem to be pretty different. And so where does this come from? I personally believe this is because this is indeed what people are still being taught. So this is a screenshot from Code Complete, a pretty famous book, two-time winner of some award. And it clearly says on one page, C++, an object-oriented language founded on C. And yes, the book is from 2004. Perhaps this is just too old. But there's another web page, one of many that I found, Learn CPP, subtitle, Tutorials to help you master C++ and object-oriented programming. And I believe this is just very deeply embedded in the minds of people. So just a few weeks ago, there was a CPP cast, you know, Phil, the other cast, with Brett Larson. And I think it just slipped his tongue. I don't know if you thought about this a long time. He said, overall, you can get up and running pretty quickly with an object-oriented programming language like C++. This made me thinking, is this really so embedded in the minds of people? And how true is it today? I believe that approximately 70% of my students would indeed agree. C++ is an object-oriented programming language, and that to some extent explains the designs that I see. But hasn't C++ changed in some way? I believe so. There is evidence in the talks that we see. So this is one of the talks that you probably know. Inheritance is the base class of evil. One of the most famous talks from 2013, in which Jean Parent actually tells us that he does not particularly like inheritance, that they found this to be a big problem. But this is not the only talk. There was another one in 2019 at CPBCon. John Cobb gave a talk on object-oriented programming in the Back to Basics track. And surprisingly, he started very, very negatively. So he started like, you would not have believed that I submit such a talk to CPBCon. The cool kids aren't talking about object-oriented programming anymore. Well, I'm still doing it because there's so much legacy code out there. And there's even other talks that are even more pessimistic. Object-oriented programming is dead. I think this title is mainly to sell the talk. It's probably not dead, but it shows a general attitude. An attitude that C++ is indeed not really in love with object-oriented programming anymore. There's other talks. This is a talk that you definitely also know, C++ Seasoning, given by Jean Parent also, with the famous slide that you should not use any kind of raw loops. And there's other talks also. Jonathan Bucara telling us about algorithms. 1 hour just about STL algorithms. And other talks like Connor Högstra, who does the same thing, a little different style. Or perhaps Kevlin Henney, talking about functional C++, totally different style. And Kevlin might not have realized it, but functional programming is not just great, it is also for fun and profit, as Phil remarked. So apparently there is a totally different way that people see the language and design with C++. Let's take a look at Wikipedia. Wikipedia is the page that should know everything about C++, at least conceptually. And on the right-hand side, it says C++, paradigms, multi-paradigm, procedural, functional, object-oriented, generic. Which of course leaves you a little wondered. What does this mean? What is this actually about? How should I use the language? And this is exactly what I'd like to go into. What does C++ mean today? How do we design code in C++ today? What are the big advantages? So let's talk about modern C++ design. So I've learned one thing in CPP chat, that is that everybody needs a disclaimer. So I have one on my own. First of all, I'm definitely not giving a complete answer to any of these complex questions. C++ is way too complex to give a complete answer. Then I also, when I now do a design exploration, I only consider solutions with dynamic polymorphism. In total, of course, the design space is much, much bigger. There's many, many more options. I mainly focus on a few, 7 dynamic polymorphism options. It's only some solutions also. Yeah, there is more, definitely. In 60 minutes, I simply cannot talk about anymore. 7 is already pretty challenging. And I only consider the current state of C++. So some of you might know there is already more. We can do more in C++ 20. We will be able to do more after that too. I will take a look at the current state. And from what I see in the trainings, this is currently still C++ 17. There will be a lot of code. Indeed, I will show a lot of slides containing a lot of code. Do not sweat the details, though. It's not about the details, it's mainly about the design. And I try to point out the most important points such that you will be able to follow even if you cannot read everything. That's also hardly necessary. And I deliberately choose a simple toy problem, a problem that you can all follow. I indeed want to talk about design and a complex problem which just messed this up. So my toy problem for this evening is drawing shapes. Yeah, I know. It is simple. It's probably, you've probably drawn more shapes in your life than you ever wanted, but it still serves the purpose. Yeah, we can now explore how to draw shapes with different approaches, different design ideas. And the first solution that I would like to show you is a good old solution. I call this a procedural solution. So I, first of all, start with an enumeration. I call it shape type. Right now, we have circles and squares. This shape type enumeration is now used in a class shape. This is now supposed to be a base class, so I have a virtual destructor. This one, however, is a little special. In the constructor, it accepts a shape type, and it stores this shape type as a data member. So it remembers what it has been set to. It remembers whether it's circle or square at this point. Then this base class is used to implement a circle, as you might have guessed. The circle class, of course, takes a radius, but the first thing in the constructor is the initialization with the enumerator circle. I'm a circle. I should initialize myself as circle. I should remember that I'm a circle. Of course, I initialize my radius, potentially more data members like the center point, etc., etc. There's a couple of getter functions, get radius, get center, get rotation, all the things that I need to get the information from a circle. And as, of course, the data members, probably encapsulated, radius, the center point, perhaps any kind of a quaternion to reflect the rotation, etc. Then, of course, I want to have a couple of operations. Say I want to be able to translate a shape. I want to be able to rotate. And I also want to be able to draw the shape. Now, that circle, there's, of course, also square, which is just there to have at least 2. Essentially, it's the same thing. The major difference is that I initialize it with square, the square enumerator. So this time, the shape remembers that it's a square. And a square, as I said, is very similar, slightly different data members, but essentially, it's the same implementation details and the same functionality. Now, with this approach, drawing an entire vector of shapes, reflected here as a std vector of std unique pointers of shape, would approximately look like this. A for loop that traverses all these shapes. Now, I don't know exactly what these shapes are, so I have to ask them explicitly, switch. So what are you? Are you a circle? Well, in that case, I have to draw a circle, which of course is accompanied by a static cast to circle pointer. Or do you happen to be a square? Well, in that case, of course, I need to draw a square. So I do the according cast and call the appropriate draw function. Now this is used, a small example, main function. I have something that I call shapes. This is a vector of unique pointers of shape, and I fill it with a couple of shapes. So I need a circle, radius 2.0. I need a square, side length 1.5, and a second circle. Why not? So we can add any number of shapes and then draw them. And this will draw probably these 3 shapes. Now, I guess you've seen this kind of code before, so perhaps you can join me to evaluate it. I want to evaluate it in 5 different categories. My scale is now from 1, which is supposed to be very bad, to full 9. This is very good. Can it get much better? And the categories I have is, first of all, how easy is it to add different kinds of shapes? This is one version of the open-close principle. But the open-close principle can also be applied to how easy is it to add operations. And then the third one is separation of concerns, a single responsibility principle. Now, I said single responsibility and I said open-close principle. I hope you have an idea where this comes from. This is the first 2 of the so-called solid principles. So the first one is the single responsibility principle, which basically says that everything should be as separated as possible. Things that do not belong together should be separated. The second one, the open-close principle, states that we should be able to add new things without having to modify existing code. So open for extension, closed for modification. The third one, just to be complete, is the Liskov substitution principle. Things should be substitutable. The expected behavior should work. We'll not need this in this particular talk. But the fourth one might be interesting, the interface segregation principle. Interfaces should not induce unnecessary dependencies. Interfaces should be client-specific, also as segregated as possible. And the fifth one, also for the sake of completeness, the dependency inversion principle. Now, I'm using the first 2 in my column, so this is the first 3 criteria. The fourth one is ease of use. What I have in mind here is how easy is it to use it in the main function, for instance, but also how easy is it to actually follow the rules of this coding scheme. So if I add shapes or if I add operations, how easy can I do that? And the last one is, of course, it wouldn't be a C++ talk without performance. Now, the enum solution, as I've presented it before, how easy can I add shapes? This is probably, as you hopefully know, not exactly what this solution is good at. This is a full 1. Full 1 means it doesn't get any worse. If I try to add a new kind of shape, first of all, I have to touch the enumeration, which means that everything that knows the enumeration is kind of changing the circle, squares, and so I kind of touch everything. But the worst part is indeed the draw function, as you've seen before, the draw function that draws a whole bunch of shapes. The switch statement. The switch statement itself is perhaps not the problem, but this switch statement will occur many times in my code. How can I be sure that I really changed all the places, that I adapted all the places when a new shape occurs? It's a maintenance nightmare. And so this is indeed the worst kind of thing that I can imagine. However, perhaps surprisingly, adding operations is not too bad. This is what I would personally rate with a 7. It's not particularly pleasant because there's a lot of copy and paste involved, I guess, but it's relatively so simple. I want to serialize shapes. Well, draw is my example. I can just add new code, a serialize function that deals with all the shapes, which, however, of course, extends my maintenance nightmare. The separation of concerns, well, it's somewhere in the middle. It's perhaps a little harder to explain at this point. You've not seen the other solutions, but there's definitely much better ways to separate concerns. So right now, all the different things are a little baked together. They're not really independent of each other, not really isolated, but it's also not too bad. So I decided on a neutral value of 5. Ease of use, well, that's not too bad. I give it a 6. It's easy to understand, easy enough. And once you know that how to add operations, this is something that you can do also reasonably well. Now, there is a reason that this solution is in my presentation. You might have thought, oh my, who uses this kind of code nowadays? but in fact, there is quite a lot of people because of the performance. So I'm also showing a couple of performance results, but of course, this involves benchmarks. Benchmarks. Benchmarks are always a little difficult, simply because there's at least one person in the room that always complains about the benchmarks. So I try to really highlight what I'm doing here. So first of all, the machine I'm using is a MacBook Pro 13-inch, nothing special. So with an Intel Core i7 2.7 gigahertz CPU and 16 gigabytes of RAM. I'm simply using C++ 17.03 and dndebug as compilation flags, also nothing fancy. I'm creating 100 random shapes. Random means I actually don't know the exact number. Could be 49 circles and 51 squares. Could be the other way around. I don't know. But then also the compiler doesn't know. And I'm doing 2.5 million updates for every single shape. Now, when I say update, what do I have in mind? Well, actually, I'm not really interested in doing anything at all. What I'm really interested in is how efficient is a solution? How much overhead does a solution come with? So what I'm benchmarking here is something like the translate operation, something really cheap, something that does not add any kind of overhead. That really shows me how expensive the solution itself is. So how much overhead do you get through pointers, through virtual functions, through indirections, similar things. So it should be a very, very simple thing to, cheap thing to benchmark. All right, so perhaps this marks down what I have in mind here, how the benchmarks work. The enum solution is actually pretty fast. I do not have absolute numbers here. I normalize everything to one. I normalize everything to the enum solution. I now say this is my baseline. However, you see from the scale of this graph that it will not be bad. On the contrary, this will be one of the fastest solutions that I can offer you. In other words, there is a very good reason that people use this solution. So GCC is a little faster than Clang. This is not a major topic here. I simply distinguish between the two that you see, okay, there is variations possible. And sometimes this really makes a big difference. This is when I point it out explicitly. All right, so this is the baseline. Let's say this is performance 1, and let's take a look at other solutions. Because when I've presented the first solution, some of you definitely had one thought in mind, one keyword of good old C++, virtual. Why doesn't the guy use a virtual function? Well, okay, I didn't show you the performance number. I give it a full 9, and you will see there's not a lot of better things. All right, let's introduce virtual functions instead, and let's see how this changes things. Let's take a look at a classic object-oriented solution. So there is no enumeration anymore. The enumeration is totally gone, nothing left. The shape type has changed accordingly. No need to initialize it anymore, so the default constructor doesn't take anything anymore. Okay, there is no other constructor also. And I have virtual functions for translate, rotate, and draw. Pure virtual in the base class, they need to be implemented by deriving classes. The circle, of course, makes this happen. The circle class, first of all, properly initializes all its data members, etc., etc. But it also implements, properly overwrites, translate, rotate, and draw. So, non-surprisingly, the square is doing exactly the same. Also, no need to initialize any kind of base class. This is happening automatically, and I implement translate, rotate, and draw accordingly. All right. The draw function suddenly is really, really beautiful. Draw is merely doing a for loop of all the shapes, and I simply call draw. Draw yourself. This function is now perfectly adhering to this open-close principle. I don't have to change it anymore whenever I add a new kind of shape. This is a definitive improvement of the first solution. The main function, however, is totally unchanged. It's still exactly the same piece of code, a vector of unique pointers that I fill with a couple of calls to make unique. It's again one circle, a square, and a circle to demonstrate it. All right, so what does this change? How does this compare to the previous solution? First of all, we have now changed something pretty profoundly. So it's not just another solution, it's a kind of a different solution space. Because what we're now able to do is we're able to easily add new kinds of shapes. This is what object-oriented programming can really do very, very well. I'm interested in a rectangle. I simply add the piece of code that I need. So as a rectangle class with all the implementations, I added at one line in the main function, I'm done. Perfect. This is what the OCP wants to see. However, perhaps surprisingly, I have to downrate the additional operations quite considerably. It is not easy anymore to add new operations. I would have to change the base class, and I might not even have access to the base class. So virtual function can only be added by one person. That is the author of the shape base class. So this is not easy anymore. And I would have to adapt all deriving classes if I do it, potentially right away if it's a pure virtual function. It's not a maintenance nightmare, but it's definitely not a pleasant exercise. The separation of concerns, well, I feel this is going down. It is going down considerably because in this solution, I assume that the implementation of the draw function, the implementation of all the functions is now part of the shape itself. This is not a particularly good idea. I would like to separate the concern of how to draw from what is a circle, what is a rectangle, a square, whatever I have. This implementation should not go into the class itself. This is why I wrote it down to 2. This is a severe breach of SRP. Ease of use, well, I feel it's kind of the same. It's easy, it's the same thing to understand. It's the same thing to use. It's approximately the same. So I also give it a 6. Performance. The performance is a little worse, as you may expect. I have to admit that I was actually happy to see that it's not totally devastating. It's approximately 30% more expensive than the enum solution. 30% is not a little bit, so this explains full well why the enum solution is favored by many people. But for other people, this is perhaps perfectly okay. Again, GCC is slightly faster than Clang for this particular case. So approximately 30% overhead. For that reason, however, because for C++ developer, 30% is not a little bit, I downgraded to 6. It's not as fast as anymore as I would like to have it. Still, I feel at this point, comparing these two solutions is not entirely fair. They are in different axes in the solution space. The enum solution is great at adding operations. It's not great, but it's definitely okay. And the OO solution is great in adding shapes, different types of things. It's hard to compare them. However, this is the classic solutions. And this is what I indeed still see in code pretty often. And you would not see how deep inheritance hierarchies can get, so how deep these OO solutions really reach. But is this really what we do today? How we approach the problem today? Well, I now try to find better solutions. First, for the enum case, where I can easily add operations, and second, for the OO case, where I can add shapes easily. And I want to address the enum case first. I want to have another solution that allows me to add operations really easy and improve on all the other values, if possible. The first thing that comes to mind is actually another classic solution, the so-called visitor design pattern. So I now indulge you for just a couple of minutes with a short explanation of what visitor is actually trying to achieve. Now, this is copied from the so-called Gang of 4 book, the book that teaches us 23 classic design patterns. It appeared in 1995, so it indeed is a classic. And this is one of the design patterns that is used most often for the following problem. On the right-hand side, I have an inheritance hierarchy that is in the book called an element hierarchy. So for our purposes, this is now shapes. I have shapes, different kinds of shapes, circles, squares, and then I also assume that I have a couple of others. It's not just 2, let's say there's 5 or perhaps even 10. However, I also assume that this is all that I will ever need. I only need these 10, and I'm absolutely certain about that. So I have all the types of shape, but I do not yet have all the possible operations on these shapes. So for instance, I cannot yet draw them. I cannot serialize them. I cannot rotate them. I cannot translate them, resize. There may be many, many operations missing from shapes. Whenever I add an operation to shape, I have to change the entire hierarchy. And this is what I would like to get rid of. I would like to add operations without having to touch the right-hand side hierarchy. And this is where this visitor hierarchy on the left-hand side comes into play. Now, traditionally, visitor is the name for the base class. The deriving classes are now operations. Now, I also give them concrete names like rotate and draw. Draw, our toy problem again. The visitor base class comes with a visit function for every shape that I know. This is my basic assumption. I already know all the shapes. I know about circles, I know about squares, and all the 10 other shapes that I currently have. There's one visit function for all of them. And now I can implement these visit functions in deriving classes. Let's say we want to rotate. I simply implement all the visit functions separately in a specific class. I want a new operation, I add another one. Implement the visit function by just adding code. This is again the idea of OCP. I want to add new behavior, I want to add new things without having to modify existing code. In order to make this visitor work, on the right-hand side, I have to add one more function, and that's the very last one. It's traditionally called accept. Accept accepts a visitor, and accept is implemented in all deriving classes with virtually exactly the same piece of code, visit me. So visit this. It is the same code in all deriving classes, but of course the type of this point is different. So I dispatch from here to one specific visit function, and from there I go to the according implementation in the given visitor. So this is the basic idea. I assume on the right-hand side a closed set of shapes, and on the left-hand side an open set of operations. This is how I can easily add new operations to all shapes. Now, it comes with a couple of disadvantages, as we'll see in a second. So the first disadvantage, once again, I have a closed set on the right-hand side. I better not add new kinds of shape. That would, of course, create a heavy burden on the left-hand side. And the second disadvantage, well, there's quite a number of virtual functions and pointers and indirections. The first virtual function usually is the accept function. I pass some visitor to accept. I go here. This is the second call to virtual function, visit. Depending on what kind of shape I really am, I arrive here after two virtual function calls. So this is something that we'll probably see in the performance. So how does this look like in code? I now apply the visitor to the example that I had before. So first of all, I have two forward declarations for circle and square. Because as I said, I know them anyway, and I need them in order to implement my visitor. Visitor knows about circles and squares and provides a visit function for all of them. Then there is the shape base class. There is no operation other than accept in this anymore. So I did a complete refactoring. Accept is the only virtual function other than the destructor that is left. All operations are now implemented via visitors. The circle, still deriving publicly from shape, has to implement the accept function. And that's the major difference now. Everything else is virtually the same. There's no draw, translate, or rotate function anymore, but accept. But it implements this by simply passing this to the given visitor. And square, no surprise, it's again the same. It implements accept by passing itself to the given visitor. Now, I can add operations. For instance, drawing. Draw is a visitor. It implements the according functions. And so I can implement my draw or shapes function, so the draw function that accepts a vector of shapes, by simply traversing all the shapes, calling accept on every single one, and passing draw. Note that I indeed pass draw a new draw for every single operation. Traditionally, again, it is possible to, of course, allocate this pass one draw to every single one. This actually pays off in our favor. This is not a bad thing. Draw is far too cheap to pay on any overhead here in the construction. So it may be an exceptional case. It may be a little too simple. But you will see it could be worse. The main function still did not change at all. I still have a vector of unique pointers that I fill with circles, squares, etc., all the kinds of shapes that I have, and I simply call draw. So from a usage point of view, it's still exactly the same. No surprises here. Okay. Now you're probably interested in how this compares to the other solutions that we had so far. I said that I would like to compete with the enum solution. And so yes, adding shapes is something that does not work well. I gave it a 2 because it is not pleasant at all. It's more like the 2 here. It's not a maintenance nightmare though. So at least the compiler will tell us, oh, you're missing something here. You're missing something here. You're not running into potentially an infinite maintenance nightmare. All right, adding operations, pretty good. Pretty good because we are able to add operations at will. Adding a piece of code without changing anything that it currently exists. I also like the separation of concerns, pretty much. Drawing, serializing, all those things that might actually draw in a couple of new dependencies are now separated from the actual shapes. Shapes do not have to know about all the details, about all the things that are now done with them. This is very nice. This is almost full adherence to the single responsibility principle. Ease of use, okay, this is what I do not like particularly. A visitor is something that people don't like because it's pretty complex. And indeed, there's a lot of things that I have to think about. There's a lot of hierarchies that I have to understand. So at least the 2 here, and these might be deeper than I showed here. It is not as pleasant to use in the real world. Now, the performance, okay, I already made a couple of remarks that we can expect that this is not going to be a particularly fast solution. And indeed, this is a solution that really hits us. It's approximately 2.5 times more expensive if we use GCC, and Clang is even more expensive. So we are paying very, very heavily for being able to add operations in a more, in a nicer way. So if you complained about the Eamon solution before, well, there's an alternative, but you're paying for this quite badly. It just adds all up. There's a lot of pointers. There's a lot of indirections. There's always 2 virtual function calls. There's not a lot of potential for optimization. And so, no, unfortunately, it is really expensive. Well, of course, the classic visitor has a couple of advantages. There is, of course, a reason that people also use this solution. But wouldn't it be great if modern C++ would give us a completely different design approach? Something that is much faster, much easier to use, and easier to comprehend? Well, I believe right now there is another thing floating in your mind. A new class that has been added in C++ 17. And I believe you're thinking about, okay, what do you want to show here? Okay, yeah, of course, the performance number. I give it a 1. It's the most expensive thing that you will see, the slowest thing that you will see. All right, so what you're thinking about is, of course, something based on standard variant. I know refactoring, and I'm trying to implement the same thing, the same idea that I can easily add operations by means of a std variant. First of all, I refactor the circle quite a bit. You notice there is no base class anymore. And you also notice there is no virtual function anymore. There's nothing that actually catches your eye. This is a really boring circle. Okay, it has a radius, it has a couple of further data members, and I have the according getters. This is code that I can show in a beginner's training on, let's say, day 3 or perhaps 4. Look here, a constructor, an initialize list, getters, data members. The square is also really simple. Same thing, no base class and only things that are really easy to understand, easy to reason about. Pretty cool. Draw is a class now that is no longer depending on any base class. No visitor. It is just a class with a couple of function call operators. One for circle, one for square. So this is how I draw circles. This is how I draw squares. The shape base class is no more. I'd have something different. A variant of a circle and a square. This is actually what I have in mind about a shape. And so the base class is replaced by a type def using alias, a type alias on variant. And if this is a shape, then I actually do no longer need a vector of shape pointers. I am already able to add different kinds of things into a vector. So I have a vector of shape. And if I want to draw all the shapes, I traverse them. And I, of course, use std_visit. I use draw, I pass the variant, and I'll do the right thing, perhaps a little magically. I'll show you how this works in a second. In the main function, I now see big improvement. For the very first time, I actually now changed the main function, and it's so much easier. I have a vector of shapes, variants, values. And since this is values, I no longer have to create a pointer to that. So I create circles and squares and all the other shapes that I potentially have. Just like that. I add them to the vector with a pushback, and that's it. Splendidly, isn't it? Amazing. It is really, really simple. There is no memory allocations anymore, no pointers. It is really the simplest thing that you can imagine. Yeah. Now, how does this compare to the other solutions so far? So the addition of shapes is not something that works well either. No, also std_variant makes the assumption that you know all the things that you want to store in it. If you try to change that, you will have to work through a lot of code. It's a little more pleasant though. I do not mean the error messages. No. They are horrible, but still you will get a slightly better experience making that happen. Addition of operations, however, oh, amazing. This is the simplest thing I can imagine. Yes, I know some of you might argue that it could be simpler, that there's still some code overhead, they have to type too much, but the action itself, adding a new class with just necessary operations for all the available shapes, there's probably nothing simpler than that. It is really, really beautiful. Separation of concerns, well, also a little more beautiful than before because it's simpler. Always would rate it with a full 9. Yes, up ahead is something that even works better, but for now, this is actually pretty amazing. And now, if you reason about this, the main function and understanding how the code works, adding new operations, yeah, after you've seen the example, I believe you could do this very, very easily. So also, this is the simplest thing that you can do. This is something that indeed you can teach in a beginner course. You do not explain the magic of std_visit, but you can tell them, okay, add an operation, copy and paste, it will work. Now, the performance is, yeah, I have to tell you, this is a slightly more complex story, unfortunately. When I used std_variant, I got this result. And I have to admit, I was really disappointed and a little surprised. This is why I checked a couple of times. Now this is the performance. It is approximately 75% slower than the enum solution. I would have expected that it is somewhere close to the enum solution, and I would have been very happy to report that. It is not. std_variant is unfortunately not exactly what we probably wish for from a performance point of view. So neither in GCC nor in Clang. The reason for that is that the way they have to handle the dispatch is a little more difficult. Difficult for the compiler to optimize later. So you don't have to understand this code now. This is for later reference. What they create internally is a table of function pointers. These function pointers are created by the means of a couple of lambdas. Okay, nice trick. However, there is a table of function pointers. If I know what is stored inside, I can grab the right function pointer and then call the right function. I dispatch by means of a function pointer. That, however, means that there's overhead. I have to grab the right pointer. I cannot inline the functions. And that, unfortunately, is not the best thing for the compiler. There's not too much optimization detail, optimization opportunity. But I tried something else. I tried another variant implementation. And there's a couple. There is Boost variant, there is Absel variant, and there's also a free variant from Michael Park. So if you go to mpark variant, to his GitHub repo, you'll find a variant that also works with C++11 and 14. So something that is perhaps useful for you even today if you cannot use C++17. mpark variant was a surprise. mpark variant is really fast, surprisingly fast. First of all, with GCC, it's approximately 5 to 10% faster than the Enum solution. With Clang, it is 40% approximately faster than the fastest Enum solution, which is absolutely fantastic. The difference between mpark variant and std variant is in the implementation of how it handles the dispatch. This is how mpark variant is doing it. A switch statement. So this is directly copied from the mpark variant. There is a lot of return statements, so for all up to 32 different cases. So as long as you do not use more than 32 types in the variant, it will actually dispatch directly by means of a switch statement. And that is much more friendly, much friendly for the compiler. The compiler can actually inline the function that you want to call. It's not behind some mysterious function pointer. And in combination with all the rest, everything is stored as values in a vector. There is no pointers, no indirections, and function inlining. This is actually the best that the compiler can hope for. And so performance is really, really great. Now, for that reason, I'm cheating a little bit. I give it a 9. True, std variant is not a 9. I totally agree. But perhaps if we take this plus the other value, take the average, then it may end up perhaps somewhere where the Enum solution is. And I said this was a 9. So it basically just depends on which kind of implementation you use for your purposes. That's already fantastic. That is something that you can do today in modern C++. Now this is the one axis of design. I now can very easily add operations, but I can still not particularly easily add different kinds of shapes. I would like to do this as well. For that purpose, I need another design approach. I need something that allows me to easily add shapes without sacrificing too much in the other categories. The next classic solution I would like to show you is, okay, intermediate thing. Yes. So std variant, what kind of solution is that? So this is a question that you might indeed have in mind. Mateusz Pusch actually tried to answer that. So Mateusz argued that the variance-based solution is more a functional approach than it is an OO approach. Well, if you take a look at this, perhaps, but perhaps not. Perhaps it's also more procedural if you take a look at the mpark variant. Perhaps there's also a little bit of OO in there, so I think it's not particularly easy to answer. But one of the things that the solution has is a lot of positive side effects. So there is no pointers, as I said. There's no virtual functions, no manual allocations whatsoever. The only thing allocating is the vector itself, standard vector of shapes. Then it is very cache efficient because I'm storing values, value semantics. This is indeed a good thing in this case. It usually always is. SRP and OCP are fulfilled almost perfectly, and I promote loose coupling. Very little dependencies to other things. I can combine this with a lot of different things. These all add up to simple code. It is indeed much, much simpler to reason about, to comprehend. And I believe this is the major point of modern C++ design. This is what Herb has been talking about for years now. every CPBCon in his keynote, he stresses the fact that we're trying to simplify C++. Paradoxically, by adding new things. We add new things in order to give you things that are simpler to use, simpler to comprehend. Now, the old stuff still works. This is why C++ grows. But you can also switch now to the simpler things. So, to just also give Jason the opportunity to show up, indeed, great C++ is trivial. Great C++ is as simple as possible. Okay, true. I know that he has something different here in mind, but the title is just very, very accurate for what I'll try to tell you. All right, I promised you another solution, a solution that is now going in the direction of allowing me to add different types easily. And one of the design patterns, one of these classic 23 design patterns that comes to mind is the strategy design pattern. Strategy. Again, I indulge you for just 2 minutes by giving you an idea what strategy is supposed to solve. Strategy tries to give you the ability to, at runtime, configure the behavior of something. So in the book, it says context. Now, this context, for all purposes, is again the shape. And I would like to configure how a shape draws itself. For that purpose, a shape is given a strategy. And a strategy, that I call draw strategy, is, first of all, a base class that implements draw. Now, it doesn't implement it, it provides the interface for a draw function. Now, this interface, one of these is passed to shape. Shape owns one of these. Whenever shape is the draw function of a shape is called, I essentially end up here. Now, by this extraction of this logic, I can now implement different kinds of strategies. I can implement drawing for testing purposes. I can implement drawing by OpenGL, by VTK, by any other graphics library that I have in mind. This aspect is now totally separated from shapes. No more implementation details about drawing inside the shape. So I can now add runtime configure shapes. And this is how it looks like in code. Again, I start with 2 forward declarations in order to be able to define the draw strategy. This is now the base class for drawing. I can draw circles and I can draw squares. That's the first step, the base class for drawing. The shape base class is back to where we ended up with in the OO solution. It is a pretty simple base class that just provides me with the interface for all the operations that are available. I can translate, I can rotate, I can draw. This was my example, my toy functions. The circle class now again inherits from shape. In the constructor, it is not just given the radius, it is also given one of these draw strategies. I am passing a unique pointer to a draw strategy. The circle now takes ownership of this and stores this draw strategy inside itself. It becomes a data member. Whenever draw is called, I now forward the request to my draw strategy. I call the draw function of my draw strategy, and I am drawn accordingly. So this is the new addition. I change and adapt the draw function. I have a new data member. The square class is, again, almost the same. It gets a draw strategy in the constructor. The draw function is adapted accordingly, and I have a new data member that stores this draw strategy. Because of that, the draw function actually does not change in comparison to the OO solution that I've shown before. I traverse a vector of unique pointers of shape, and I draw every single one of them by simply calling the draw function. It just happens that the draw implementation is no longer part of the shape. It has been extracted by means of the strategy. And I can now implement this as I seem fit. I can have an OpenGL strategy, which is able to draw circles and squares accordingly. So, whatever. The main function is changed because at this point, I am actually required to provide at construction something that allows me to draw the thing. So I am passing a unique pointer to an OpenGL strategy to all 3 shapes that I'm creating, the circle, the square, and the other circle. I know it looks a little bit like overkill. I'm creating the same OpenGL strategy for every single one of them. That's not the problem. In this particular case, we could optimize. Perhaps you feel like a shared strategy might be better. That's the strength of strategy in the end. Every single one can be configured individually. I could use different kinds of strategies here. I draw them, and again, I see the according output. Did you notice that actually I introduced deliberately a very common design bug? Let's revisit this draw strategy. The draw strategy can draw circles and squares. This sounds like a very reasonable idea. And of course, I can draw both. So why not put them together? Actually, this is now a violation of the so-called interface segregation principle, the fourth of these solid principles. I should not put together things that do not really belong together. Why? Imagine that I add a new kind of shape. I would extend this draw strategy again. I would simply add a new kind of a new draw function, essentially. This, however, has again an effect on circles and on squares and all the other existing shapes simply because they know the draw strategy. This interface is basically known to a lot of clients, but every client only needs one of these functions, not the rest. So changes are always visible everywhere. In order to fix that, I simply split this. I need two different draw strategies. I need a draw circle strategy and I need a draw square strategy. A draw strategy, one single draw strategy for both of them. The first takes a circle, the second is square. And this is, of course, now what I use inside circle. So this one, the circle gets a unique pointer to draw circle strategy and stores it accordingly. And no surprise, the square gets a draw square strategy and stores it accordingly. That is the right solution. This is proper dependency management. This is what the solid principles ask us to do. Now, of course, I implement different OpenGL strategies, one for circle, one for square. Also, this is a separate, and I create the according strategy in the main function. All right. Now, how does this compare to what we've seen before? Adding shapes is actually not bad, but a little more complex than in the previous OO solution. Now I always have to also add another strategy, the according draw strategy, and consider that there is more, that there's not just drawing, that there's also serialization and potentially more operations. It's quite a lot of work. I can do this nicely, separately, by just adding code, but it's not as pleasant as it was before. Adding operations, okay, not any better than the OO solution. This was not to be expected. It is against and still hard to add operations. I cannot change the base class easily. Potentially, I cannot do this at all. The separation of concerns is now better. In comparison to the OO solution, which was just a 2, I am now up to a 7. Now, drawing, serialization, all the operations that I have in mind are nicely separated, extracted. However, they're still coupled to the shapes itself. So I can draw, I can potentially serialize and rotate and translate whatever I have in mind, the shapes. It is still known to a shape what it can do. It's just the implementation that I extracted. Also, a 7 sounds about right. Ease of use, well, I feel it's not easy to really use, not as easy as I would like it to be. It indeed comes with quite some overhead. First of all, you've seen the main function. Now I always have to do more. I have to create more stuff. I have to deal with these strategies, and there may be potentially more. I also do not particularly like the fact that I've added so much different things, so much different details. It just is harder to really comprehend in its entirety. And the performance, well, not too good also. It's not as bad as a visitor, but it points in the same direction. Again, 2 virtual function calls per operation. I call one virtual function, so the virtual function on the shape, and it forwards it to a second virtual function in the strategy object. So, and again, Clang performs a little better than, GCC performs a little better than Clang in this particular case. It's the same structure as up here. Well, same general problem. Well, isn't there something in C++, a modern way to express the same thing more easily, with less errors, less overhead, something that perhaps allows me to decouple more? Well, there is. Essentially, the strategy object, this strategy class, is nothing but a single virtual function. This is something that I could actually extract something. Okay, I again forgot to show you the two, performance 2. I could actually now lean on a std function. I could entirely extract the aspect and simply say, well, all I need is a function to call. The std function is quite a nice replacement for just that. So my draw circle strategy, my draw square strategy become function objects with the according signature. In this case, it is really hard to mess the ISP up. Std function is just one function. I cannot accidentally put two of these in the same thing and violate the interface segregation principle. So this is a bonus point in this case. The shape, totally unchanged, nothing new here. I still have the 3 operations that we saw before. And I have to adapt circle now a little bit. Instead of a unique pointer to some base class, I accept a value, a std function that I probably move into my own data member. The first thing is, it is obviously easy to comprehend. There's no lifetime issues, for instance. Sure, a unique pointer is also something that helps me here a lot. But as soon as I copy value, I do not assume that there's any kind of problem under the hood. This is a nice thing, a nice simplification. All right, the rest is the same, and also square is adapted accordingly. I pass a value in the constructor, I remember the value. Whenever draw is called, I simply forward the request to my std function object, the value. Draw is unchanged, so I skip it. I have different kinds of operations, again, so different kinds of implementation. I now, again, choose OpenGL. I now choose a class OpenGL circle strategy with a function called operator. This now allows me to implement how to draw a circle by means of OpenGL, and something similar for squares allows me to draw squares with OpenGL. And this is what I apply. It becomes a little simpler. It becomes a little simpler because I actually do not have to make unique one of these strategies anymore. I just create an object right away. So this is how you should draw yourself. I pass it to the constructor. There is an implicit conversion to a std function object, and then I'm fine. It's a little easier from a usage point of view. So, in order to demonstrate that this is indeed an improvement, I now play a little bit with this. So first of all, I don't have a base class anymore that tells me that I have to implement this as a class and with a virtual function. I have all the options in the world. I could simply implement this as draw functions. I have a draw circle and I have a draw for square. I could now pass the draw functions directly. Unfortunately, this does not compile because the compiler cannot figure out which of these overloaded draw functions I want to pass to the make unique function. So this is a compilation error. Now, of course, I do not want to statically cast the right function type. And of course, I also do not want to rename these functions such that this is a unique thing, that no overloading is used. For that purpose, I add a little helper, draw, capital D, a little struct, which is nothing but a stand-in for calling the draw function. So struct draw is implementing a templated call operator, and it takes any t. And what it does is simply calls draw on the given t, some drawable, something. This is now what I can pass in the main function. I simply pass draw objects, and this allows me to indeed call a free function I do not have to implement the drawing in terms of an object of this example. And it still works, because as long as I don't want to draw integers, which to do two-phase lookup would not work, as long as ADL is used, this will always find the right thing. Now, this little helper is something that can actually make defaults. So I can add a default, draw circle strategy ds is equal to draw. If I do not specify any particular strategy, well, then use that one. And of course, I do the same for square too, which now allows me to actually get rid of this second parameter. And I'm back again to the initial main function, the one where I do not have to care about how things are drawn. Now, I believe you probably complain. Probably complain because you realize, or you argue that I've now coupled a specific implementation, which of course I shouldn't do. Now, I have not coupled a particular implementation to my circles and my squares. I have coupled a particular interface. As long as you give me any implementation of a free draw function, I work. I'm absolutely fine. So this is a default interface, not a particular default implementation. And so this very nicely shows this gained simplicity, this loose coupling. I have a couple of options that in the old approach, in this classic strategy design panel, I would not have had. All right, so now with this in mind, let's compare this to the other solutions. Adding shapes is easy. Again, and I would argue a little easier. There's less things to think about, less code to write, less base classes to implement. It's a little easier. The addition of operations, well, again, it's not pleasant, but also here I rate it up a little bit because I personally feel it has become a little easier because of the way I have to implement the operations. It's perhaps at 2.5, so a slight notch, one slight upvote, but I feel it's a little better. The separation of concerns, well, also good. No improvement to strategy. I still have everything nicely separated, except for the fact that the operation itself is still visible in the shapes themselves. However, I definitely improved in a way I can use these things. I again feel it's easier to comprehend, easier to deal with, easier to use than the strategy. So I give it a 7, which is a slight upward in comparison to the initial OO solution. So slightly better from my point of view. The performance, well, I would like to show you that it's actually performing approximately as the OO solution. Unfortunately, that is not the case. I was hoping for that it is essentially the same as this, or perhaps better than that. But, well, it depends. If you use GCC, unfortunately, performance is really, really expensive. Perhaps even slightly more expensive than this visitor here. If you use Clang, on the other hand, it's not as bad. So obviously, the Clang implementation of stud function is faster and provides more optimization potential. Well, so it now depends which of these two solutions you have available, which compiler you use. If you have a GCC, you probably would argue, no, this is worse. If you have a Clang, you would probably argue, oh, this is a definitive improvement. This is much better than before. So unfortunately, depends. So I, at this point, would argue somewhere in the middle, perhaps it's a 5. It's a little worse than OO, but it's probably a little better than the strategy. So it's perhaps somewhere in the middle, 4 or 5. I couldn't decide. I would have. I used a 5. Now there's only one thing left. Now that we understood function implementation, actually there is one more thing that we can do. Once we've understood what a stud function is and how it works, we can actually indeed apply this to shapes directly. And at this point, I would indeed say it's a nuisance to have a stud function for object for every single operation that I would want to extract. There may be several. There may be drawing, there may be serialization, there may be other things that would not like to have inside the shapes themselves. I can generalize this. I can generalize this by means of the technique that is used for std function itself, by means of type erasure. So if this is the first time you see it, it may be a little fast, but I hopefully can give you an impression how it works in general. It's definitely not an in-depth introduction. So first of all, I start with circle. You see, no base class anymore. And again, you see that there's also no virtual functions whatsoever. This is, again, the simplest kind of circle that you could implement. Then, translate, rotate, and draw have now completely been extracted from a circle. I don't want to no longer want to have all the operations available here. I would like to be able to add them freely. That is easier to deal with in general, and also allows other peoples to more naturally add new operations. So free functions for all of these three. Square, again, no surprise, is essentially the same. No base class, no virtual functions anywhere, and free operations that work on square. Now the magic in this solution happens in the shape class itself. Shape is not a base class anymore. Shape acts to some extent as a container. A shape now accepts anything that qualifies as a shape. Well, what is a shape? Well, from my point of view, everything that I can translate, rotate, and draw. So, the first thing that we see in the private part of the shape is a helper struct called model. Model itself is implemented in terms of a template. So, gets a template parameter, some t. This t is stored inside this model. And the model implements all the necessary operations. I'll show in a second where this comes from. So translating, rotating, and drawing. How? By simply forwarding to the according object. So I know what my t is, and so I pass the object to the operation, and I pass all the things, the arguments accordingly. Now this is what I see as the requirements on a shape. And I formulate these requirements quite naturally in terms of a base class, which, however, is not a base class for circle or square. It is a private struct that I call concept within the shape class itself. This concept here is the base class for model. Model needs to implement translate, rotate, or do translate, do rotate, and do draw in order to do its job. This is the basic requirement, as all the base classes usually sketch out the requirements, the basic interface of a type. But note, circles and square do not have to inherit from that. Inside shape, I now store a unique pointer to a concept. In the constructor, I'm giving something, I'll show this in a second, and I can now abstract it in this form. By means of the virtual functions in the base class, I'm able to actually perform the necessary operations. Also, shape should be able to be translated, rotated, and drawn. And again, I'm using free functions. However, this time I need access to this thing here, this fella in the private part. And for that reason alone, I make this friends. They kind of belong, and I use this trick that I implement this friend inside the private part of the shape class. It is a free function. It is injected into the surrounding namespace, but it is also a friend. Now, in the constructor, as I already said, shape accepts anything, any t. It creates a new model for this t. I instantiate a new type for that, and it is a concept because any model, all the models I could possibly instantiate are concepts. I store this in the pimple pointer. It will not compile as soon as any of these types does not provide me with the given operations. The compiler will simply reject it, cannot call draw on this t, cannot call translate on this t. But as long as it compiles, this actually qualifies as shape. It has all the operations that I need. Now, in order to make this work as a value, I have to deal with the special member functions. Thanks to the unique pointer, the move operations actually work fine, but I have to deal with copy. That is a special thing. We don't have to deal with the details here. Now, drawing a vector of shapes has changed again. Again, I have a vector of values. It is not pointers anymore. I can just store my values directly in this vector. I traverse these values and I draw them. This draw function will call the friend draw that I have shown before, which then in turn calls the virtual function that forwards the request to the according draw function for the kind of shape that I currently store inside the shape object. And this is how I can use it. This is how it all works together. I have a vector of shape. I have, again, I push back a couple of circles, and this is something you've seen before. This is very, very similar to the variant solution that I've shown before. I simply create values. I push them back into the vector, which now accepts virtually anything that qualifies as a shape because of this shape class. I draw the shapes, and again, I see 3 lines of output. Really beautiful again. From a usage point of view, from a comprehensibility point of view, as long as we do not take a too close look at the implementation details of Square. And so, well, let's take a look at how this compares to the rest. Addition of shapes, well, pretty easy again, perhaps even easier, because I do not have to implement any kind of interface. If I feel like implementing rectangle, I just implement the most simple rectangle that I could possibly do. And I implement operations on this, free functions, which I can easily add to. If I feel that a third-party library type should be a shape, well, then I simply implement the according operations like draw, translate, rotate. It works too. I can really add anything that qualifies as a shape. Adding operations, okay, again, not easy, but again, easier perhaps. I have to implement, I have to change only one interface, and then I have to implement the according free functions, which I can do too, even for third-party types. So it is simplified. It is not a pleasant thing. Now, however, the separation of concerns is, again, really, really good. I no longer see all the operations in my shapes. I have them, but everything is nicely separated. A very, very loose coupling again. And I already mentioned that I really like the ease of use. It might be a little easier. We've seen the variant solution, but again, I feel this is really easy to comprehend and easy to use and to extend by new types. Now, the last number, the performance, I was actually hoping it would run pretty fast, and I was not disappointed. In comparison to the strategy and the function, stood function implementation, it's actually faster. It's approximately on the same level as the OO solution before, perhaps surprisingly. Yes, there's a little overhead, but despite the fact that there is potentially a lot going on inside this, magical shape class, it is not too heavy on the compiler. Apparently, there is more optimization potential. And definitely there is. All the values now lie nicely behind each other in the vector. No indirection anymore due to pointers. So less pointers, but probably the same number of virtual functions. So ultimately, I would give this a 6. It's approximately the same thing as the OO solution. It is comparable here. All right. 7 solutions that we have taken a look at in total. Now, my major point is, of course, the new solutions, the modern C++ design approaches. So let's summarize by taking a closer look at these 3 again. The first thing that I feel is absolutely amazing is this column here, ease of use. This is probably what the modern solutions give you. It becomes easier to reason about these things, easier to deal with them in the first place. So there is only green and high numbers. This is a good thing. Also pretty amazing is this column. SRP which is often referred to as the most important of these solid principles, is actually very, very well adhered to. High numbers also in the green. And depending on which axis of the OCP I'm on, it's also pretty good. Either I can very easily add operations like here in the variant solution, or I can again very easily add shapes like in this function or type-based solution. And last but not least, the performance. It is not amazing in the second two, but it is definitely comparable to what we had before. So we'll not have much improvement. And I actually did not mention that there is definitely more potential for optimization here. I mentioned these small object optimizations that I did not go into detail here. So the performance is not bad. On the contrary, we do not lose anything. We might gain something. And so ultimately, I consider this some kind of win. Now, what is these solutions? How has C++ developed? How can we perhaps summarize these? So what is modern C++ design? Well, Wikipedia gave us a lot of answers. So it can be procedural, object-oriented, functional, generic, and this was entitled with multi-paradigm programming. Well, hopefully you would not argue at this point, not anymore at least, that it is one of the first four. No, not really. It does not. These solutions do not are not firmly rooted in one of these four paradigms. So that apparently is what multi-paradigm is about. There is many things that are somehow coming together. Now I have to admit I have one problem with this multi-paradigm programming nowadays. If I now advertise multi-paradigm programming, that this is what you truly should use today, then to some extent it sounds a little bit like you have to choose. So as an example, there has been a great talk, another talk, there has been so many, at CPUCon 2019 given by Matt Gottpold. So he compared different styles of C++, an object-oriented solution, a functional programming solution, and a data-oriented design for a path tracing application. If I now say multi-paradigm, perhaps this is what pops into mind. Oh, now I have to choose between A, B, or C. No, this is definitely not what I have in mind. What I really have in mind that is that we kind of don't care about the paradigm anymore. I feel like we're just using the best parts of every paradigm, mix them, and come up with something that is just better. And so indeed, I don't want to talk about paradigms anymore. It's no paradigm programming. We pick the best ideas of all the things that we have learned in the past 40 years of C++, create something new from it, and indeed we gain, especially in terms of simplicity. Now, hopefully this gave you some idea about how modern C++ design may look like. There is indeed a lot of new approaches, a lot of things that it can do today. However, I believe half of you are now scratching their head. There's nothing new. Okay, stood function, C++ 11. Stood variant, C++ 17. You did not show us anything surprising, nothing that we've not seen before. So what? Well, if this is your thought, then you're actually in a very blessed group. The group that I would call the inner circle of C++. So let me show what I have in mind here. This is a screenshot from Bjarne's keynote talk at at CPUCon 2019, entitled C++20, C++ at 40. So the keynote talk, let's call it the anniversary talk for C++. If you pay attention here, YouTube tells you how many people have already watched it. And so it says 126,000, or close to 127,000 people have watched this talk, which sounds like an amazing number. 127,000 people have watched Bjarne's talk about C++ at 40. This sounds like a really huge number, but unfortunately, actually it's not. Officially, we have 5 to 6 million C++ developers worldwide. And this has nothing to do with the image here. No. This means that approximately 2% of C++ developers have watched Bernard talk. Now, some of you might argue, well, okay, there's more important talks than this anniversary talk. But I have to admit, I did not find a single talk that has more views. So, of course, means C++ talks. Even the talks that I would consider more famous, more important, 127,000 is a maximum. And so there is a huge number of people that do not watch talks. There is a huge number of people that probably do not go to meetups like you just do. There's a lot of people that don't read books, that do not read blogs, that do not know about these changes that we have experienced in C++ the past decade. This is the people that still implement all this stuff in the way C++ is still taught and in the way that they have learned it from the very beginning. So, you are now on a mission. You have now a better impression on how it looks like. And if you said, oh, this is not new for me, then you're especially on a mission. Tell your friends, tell your colleagues, probably especially your colleagues, tell your favorite pets, tell everyone to understand the virtues of modern C++. What is it really? No, it is not just about features. There is much more to this idea of modern C++, this philosophy. It is about reducing pointers and inheritance hierarchies because they have been bugging us for so many years. It is about introducing values much more prominently, value semantics. And it is primarily about keeping code simpler, to making it harder to introduce bugs, to making it harder to have bad design. Then you've seen 7 solutions in total, 7 different approaches to the same problem. Yes, it was tiresome, but it also shows one thing. There is no solution that fits all the problems. You need to know about different approaches, different possible solutions. And you have to pick. You have to pick them. And this is definitely easier if you have an idea about these different approaches that C++ offers you. So indeed, this idea of knowing a little functional programming, a little object-oriented programming, combining this in a clever way, that is probably the ultimate strength of what we can do today. So there is so many features, so many approaches that we can indeed focus on the good ideas. So tell them about this and tell them that I don't have to shackle about thinking about paradigm programming anymore. Oh, I'm not doing something proper if I don't use object-oriented programming. No, they should not think about any kind of paradigm programming anymore. Tell them that they should embrace no paradigm programming. That has been my talk. Thank you very much for the attention. I'm, of course, now available for a couple of questions, if this is possible, if this is working out in the stream.
Oh, we have lots of questions.
Lots of questions. Oh, no.
Yeah, well, we'll get to the questions in a moment. First of all, just wanted to thank you, Klaus, for doing an excellent job of talking into nothing. There were
Thank you.
at varying times between 83 and 92 people watching. There's still 83 now, so you've held on to them. That's great. And I know it's hard just talking into the void. I wanted to make one suggestion, which is the next time you do this talk, consider this for a title. Paradigms Lost, Paradigms Found.
That is a nice way too. I like it.
The ideas are free.
Oh, okay. That's what I was just about to ask. So I kind of also stole this title from Roland Bock, but he also said it's perfectly okay if I use it. All right. Thank you very much.
Now, that title was good too. It made me wondering what it was all going to be about. So before we get to the questions, I just wanted to show the results of our polls that we did just very quickly. The first one was, what best describes you? Are you a regular, first-timer, outside the UK? So, of course, most people were C++ London regulars, but a significant number of people tuning in from another country. So that's really nice to see. And obviously one of the benefits of doing this online. So I'm pleased about that.
Absolutely.
And then the other, let me see if I can switch over. Here we go. Which paradigm do you prefer? Now, I put this question up right at the start before you really went into the talk, and then I cut it off. So people didn't really have the benefit of tailoring it to what you said.
Yeah.
Interesting that the majority of people, or the largest number of people, prefer generic programming. Only a sample size of 22, though, so cut them off quite soon. So not really too much you can read into that, but I thought it was a fun question. Of course, a lot of people are only 9% functional. A bit disappointed in that. We'll have to work. Oh, yep. Talk about functional and it pops up. How about that?
Yeah.
Yeah, people contributing right now. Okay, so to the questions, let me actually let's put this up on the screen as well.
Right.
And if people can read that.
It's unfortunate right now you have to read it for me.
Yeah, I'm gonna actually you can stop sharing your screen for the moment and you'll be able to see
perhaps this helps
what we've got. Why is it on the polls? Q&A. Right, I'm still learning this.
All right.
We'll go through from the top rated questions, but actually before we do that, I just wanted to skip right down to here. Now, we don't usually, well, I was hoping not to get any trolls, but we had Mr. Troll turned up asking, was object-oriented programming a mistake? We won't take an answer for that question. I think that was literally just a troll. The top rated question was, I was wondering if performance would improve in the OO case if some methods were declared final and the compiler might monomorphize them. Now, that question came up when you were discussing the original OO case. I think it may apply for some of the later virtual function-based ones as well.
All right. So I have to admit I didn't try it. Would have just added to the complexity. I kind of believe that because I have random types, so random shapes, I would not expect that it makes a big difference, but I might be wrong. I could perhaps benchmark this separately, so present this in an updated version. I would expect that because the compiler has no idea of knowing what kind of shape it's currently drawing, there is no way that it can guess which function to call. Well, I didn't try it, so I cannot give you any number, unfortunately.
So you got some homework before your next version.
Yeah, absolutely.
Now, there was a bit of chat going on in the YouTube chat, which I've been trying to encourage people to use Slido for questions, but this was related to the one we just asked. Somebody was asking about why there was a difference in performance between GCC and Clang, and Gaspar Erzman actually dropped in and said his best guess was speculative devirtualization. So maybe that the compiler is working out when to devirtualize, even though you haven't put final, and that may give you a hint that there's some headroom there, I think. Yeah. The second question was actually me, and I did ask this early on. It was partially answered, but not fully, so I'll still answer it. What about compile time polymorphism for visitors? I think you sort of touched it indirectly at the end.
I touched indirectly. I just selected 7 of the classic things. There is so many more solutions. I think 7 is enough for 1 hour. I think it's already probably too much. Of course, we can also deal with other solutions, and there's always something to win for specific situations. It was just a selection that I did. I'm sorry if this was not exactly the solutions that you would have used in your context.
Yeah, no, I just thought it's worth asking the question. Might be something to think about as well, maybe to discuss in the rooms afterwards.
Don't consider these 7 to be in the entire solution space. There's really much more. I had approximately 15 on my table, and I selected the classic ones because I believe it's the easiest one to follow along.
Yeah. It was a good selection. I enjoyed it. Mr. Troll pops up again. This is voted up. This was also asked in the YouTube chat. People wanted to get hold of the code themselves and maybe benchmark it themselves. That's changed already.
So do you have? Sorry.
Do you have the code on GitHub that you used in the benchmarks?
I usually use it in my training classes,
okay.
Which means, however, it's available. I can extract it. I might send it to you in order to just forward it. Do you have any kind of?
Yeah, we have a CPP London repo, and I can put a link to it in the meetup page.
That would work pretty well.
So yeah, we'll sort that out.
All right.
Thank you.
Okay, and this is probably what I said before. Whenever I present benchmarks, there's at least one person that complains afterwards. It is always. Of course, this is one particular implementation of GCC, one of the standard library. I mean, it is GCC and Clang. It is my computer. It is a specific time of day. There's so many variables. No, nobody will have exactly the numbers I had. But at least you can run it for yourself and see what works for you. This is
right, exactly. I think that answers Gaspar's question there as well about seeing the assembly. There was a comment about compile times, that the stood variant solution will give you quadratic compile times on the number of types held in the variant.
Yep.
That wouldn't surprise me. I've seen similar things myself, and also with lambda heavy solutions as well.
Absolutely.
Tends to take a massive hit. That, of course, is a quality of compiler issue. But do you have any comments on that? Beyond that,
it is not as good as we would like it to be. But C++ never has been particularly famous for its compile time, unfortunately. Now, of course, if compile time is of serious concern in your, for instance, company, because you do not want people to just wait for 50 minutes whenever they changed one detail, then, okay, perhaps this is not the right solution. I did not experience any heavy compile times because I do not use more than 5 or 6 types in the variant. And here it was only 2, so this was hardly noticeable. But yes, I'm aware of the problem. I just cannot give any advice how to improve the situation here.
My advice would be to join the committee and help push through language level variant.
This is
in probably C++ 26.
This is something that perhaps might make the difference. But yeah, you also said it. I don't expect that this will come anytime soon. 26 is the earliest date that this might arrive. Yeah. But it has strong supporters, so probably something will change in this regard.
Although, while we're getting distracted by future language versions, I think there may be more chance of getting pattern matching in 23, and that may have something to say in this as well.
This is what I said also along the way. We will, so when we talked about the visitor, there is already nicer things on the horizon. Yeah, so people are already arguing that visitor is only the second best solution. But right now, today, people cannot primarily use the visitor. The variant. And so this is the state of the art. And I also said that I want to restrict me to state of the art.
My nickname for the visitor pattern is the unwelcome visitor. Let's see what else we got. Gesper again. More benchmarks. Benchmarked other implementations as stood function-like things.
No.
Okay.
Unfortunately, no. Yeah. So he basically mentions a specific reason. I didn't go into all these details. I did not benchmark anything else except for stood function. And I did make the exception with stood variant that I said, well, it is so slow that I would like to see something else. I would like to see how it can be better. And mPark variant just fitted the bill pretty nicely. It's very, very lightweight, can be downloaded and can be used under the Boost license. Unfortunately, I didn't do this for stood function. That would also be a nice idea for next version of this talk.
There is a library, I forget the name of the library now, from Eduardo Madrid, where he claims excellent performance on type erasure-based solutions. It may or may not be relevant to this. We can talk about that offline. Yep. Could be something to look into.
All right.
A lot of people saying great talk, which I concur with.
Thank you very much.
Somebody was reminiscing about the texture class in their graphics programming. I think that was quite early on in the talk. Yeah, does performance get better on newer versions of compiler versus older versions? I don't know if you have an opinion on that.
So this is what I would hope for, but let's take a look at stood function. I don't feel that this is, the GCC implementation is really, really slow in comparison to the Clang solution. But how it has been available since C++11, should have been available. And so apparently, if something changes, it changes very, very slowly. I would expect that things get better, but it might not happen. So, well, I'd like to see more improvement on that, not just improvement in terms of the new features.
Right. One thing I've noticed is that compiler optimizations and even CPU optimizations tend to evolve in tandem with what people are actually doing with real code. So if you start to use more paradigms more heavily, then things will get optimized more for those paradigms rather than let's pick the paradigm because it performs better with this particular compiler. In fact, it's more of a lockstep evolution. At least that's been my experience. Obviously, there are exceptions to that. Was object-oriented programming a mistake?
The next question is very philosophical. What's the mistake? Well, I could also go into detail about this for approximately 1 hour. There is really, really nice blog though. So I showed this one slide from the talk by John Culp. So the Back to Basics Object-Oriented Programming talk. And in this talk, in this blog that he shows on this one slide, there is more links to other talks, blog entries usually. This is definitely something worth to read up if you're interested in whether it was a mistake or not. There is a lot about the history that we indeed have forgotten. So there is a lot to it. Okay, different thing.
Again, how would you score dynamic duck typing on your grid?
Score in the sense of, okay, now it's hard to add back, right? So whether I like it or whether not like it.
I think what would its strengths and weaknesses be?
I think the type array solution is indeed just easier, and it serves and fits my bill. And so
your duck bill.
Sorry?
Your duck bill?
My duck bill.
Yeah.
So if this is what this question is in mind, I feel it is a definitely good addition to what we have. We should not just overuse it. It's the same thing with all things. As soon as you overuse it, it's probably bad again. And
I'm not sure what the purpose of that question is, but
so I've given a talk in 2017 about free functions. Some people liked it very much. Some people didn't like it at all. So my personal point on private and protected is that private is, of course, great for data members, but not for functions. Private functions are really tiny little helper functions. All the other functions should be somewhere outside from a testability point of view, mainly. So I think protected is something that I would not use a lot. I don't see the point. But private is definitely something that can be reasonable. As soon as I have any kind of invariant, I want to encapsulate this properly.
I have opinions on this too. Since you mentioned my functional C++ talk, I express those opinions in there, so go and watch that. Looks like people have been asking questions while we've been relaying them, so some of them have already jumped up. So there's one at the bottom. Are there any standard solutions now or in the upcoming future to generate a type eraser wrapper?
Oh, this would be absolutely fantastic, because this is definitely by far the worst thing about these type erased things. To always have to write a new wrapper, this type eraser class, for every abstraction I want to create. And it is surprisingly difficult to do this right. There is so many details. So right now, in a standard committee, we want to have a sort of function for a fixed size. So like how was it called? I now forgot the name. An in-place function. It is seriously difficult to get the details right. And I don't want to think about this again and again and yet again. So this would be nice. But unfortunately, I'm not aware of anything that really works for everything. There is lightweight solutions, but not heavyweight solutions upcoming.
Okay. I'm hoping that if we do ever get language level variant and pattern matching, I'm hoping they will provide the alternate solution that would make this unnecessary, but there's no guarantee of that.
No. Also, it will probably take a long time until they have agreed on how this should work, etc.
That could take a long time.
Yeah.
So I think we got through all of the questions there. There was some more discussion going on YouTube, but I haven't been able to keep up on that now. There are, for those of you that joined later and maybe didn't see the message earlier, there's a set of Jitsi rooms. If you go to live.cpplondon.org, if you're not already there, there's some Jitsi rooms linked off there where we can go to now to continue the discussion. Hopefully, Klaus will stick around and maybe visit some of those rooms so you can get a chance to talk to him. And I will walk through there as well. But for this stream, we're going to finish here, I think. Unless, Klaus, do you have any more final words to say?
No, thank you very much again for the invitation. I really appreciate it. And I hope I could repay the favor of you being 4 times in Munich. A little bit.
I may be there virtually this time. But thank you for coming. Thank you for for doing this, and excellent talk. And thank you all for tuning in. Hopefully see some of you in the GC rooms. We'll see you next time.